you ready to start? You also hear me? Okay. Good morning, everybody. Welcome to the second and unfortunately already last day of this conference. It's Saturday morning, but you all seem to be awake. I'm not sure whether there are still some other people outside and have some coffee, but I think it's better if we start now, especially as some people had yesterday problems finishing the presentations in time. So I don't want you to wait for your breakfast at 10:30. So to give you a start now, if there are some other people outside, they will, I guess, join us in a few minutes. Now this is the room where the Boost.Asio presentation will take place. I'm not sure whether there's a paper now outside, so if you want to go to the other presentation, it's obviously in the other room. But it's good that you're here, stay here, that the room is nearly full. Before I start with the presentation, I want to briefly introduce myself. My name is Boris Schäling. I'm actually German, so if you like, you can speak German to me later in the breaks, or you can even ask me questions in German. I am living and working in Amsterdam in the Netherlands. I'm working for a company in finance, a so-called market maker. That means I use C++ day in, day out to create applications which connect to exchanges in the world, like Deutsche Börse and Frankfurt, and buy and sell stuff. Now you see a lot of references here to Boost on this first slide of my presentation. The obvious reason is that this is a presentation about a Boost library. Another reason is that I'm trying to be active in the Boost community, doing a couple of things there. I'm not at the forefront, that is where the library developers are. We have some here at the conference. I only mentioned Boost Geometry or Boost Proto. I'm more in the background on the second line, trying to make sure that other people realize and understand what kind of great libraries are developed in the Boost community. So while other people write the great code, I try to write the good documentation, which means books and articles about the Boost libraries. I contributed a little bit of code. There's also a little bit of code in Boost.Asio for me, but I'm not the developer of Boost.Asio. There's a guy called Chris Kohlhoff, someone from Australia, who happens to work in the trading company in Australia too. Now, when you look at Boost.Asio, first thing we have to make sure is that you are maybe not surprised about the library name, Asio. What does that Asio mean? Well, you might have guessed already. Asio stands for Asynchronous Input-Output. If you have yesterday been at the C++ presentation, you heard that we have something in C++ called async. There's an async function, and one of the things I have to talk about first when it comes to Boost.Asio is that we all understand what asynchronous operations look like in Boost.Asio. That you don't mix up asynchronous operations in Boost.Asio with what is called async in C++ 11. So there are different concepts, and I want to make sure first in the presentation that you all understand what the concept of asynchronous operations in Boost.Asio is about. You will also see that to a certain extent Boost.Asio or libraries like Boost.Asio compete with REST. So I want to make sure we understand when we use a library like Boost.Asio and when we use REST. Of course, we are going to look at some source code. We want to see how Boost.Asio is used in our own programs. We want to see how the Boost.Asio architecture looks like. It is especially important if you look at the Boost.Asio documentation, that you can easily understand which parts of the documentation are relevant for you. And last but not least, we're going to look at some classes, functions, which are just good to know. So if you want to work with Boost.Asio after the presentation, because you will think just like me, this is one of the great Boost libraries we have, then it's hopefully easy for you to jump into the library. If you have any questions, interrupt me anytime. You don't need to wait until the end of the presentation. Just make sure until somebody passes the microphone to you. Otherwise, the organizers will get angry and at some point throw it at your head. Now we start with the presentation, and the first thing I want to talk about is what are asynchronous operations in the context of Boost.Asio. What I'm going to look at first is a synchronous operation, so not an asynchronous one, a synchronous operation. That is what you see here in the left top corner of this slide. That is a function which are called do_sync here. All of the names you see here have absolutely nothing to do with Boost.Asio. It is just about making sure that you understand what asynchronous operations look like in Boost.Asio. So here in the left corner, I assume I call a function doSync. This function should be a synchronous function. It means when I call this function and the function returns, it has done whatever it should do. And when you look at the functions you normally call in your code, basically everything is synchronous. So whenever you call a function and it returns, you know the function has done what you wanted it to do. Very simple function, everybody knows, printf. When you call printf and printf returns, you know the string has been written to a string. There's nothing to wait for anymore. Printf has done its job. And contrary, if you look at asynchronous functions or asynchronous operations, it looks a bit more complicated now, but it isn't really. Also easy to understand on an early Saturday morning. Here in this case, I assume I want to use an asynchronous operation. What I do now first is I call a function called doAsync. If you look at the error, it looks very similar to doSync. You call the function returns. On the first side, no difference. But the important difference is that when doAsync returns, you only initiated an asynchronous operation. An asynchronous operation has started, but when doAsync returns, it doesn't mean that it has been completed. Now what you normally want to do when you use these asynchronous operations, you want someone to tell you when the asynchronous operation has completed. And that's where you use a library like Boost.Asio. And libraries like Boost.Asio typically use event loops. I say library like Boost.Asio because there are many other libraries out there on the internet which work similar. So normally you hand over now the code, the thread, to a library like Boost.Asio. That is what I was trying to show you with this function call, which I call event loop. You see that when I call event loop, the error doesn't come back. At that point, I pass a thread. That is that blue arrow going down there. I pass a thread over to Boost.Asio, to the event loop in Boost.Asio. And now Boost.Asio runs some code. There's some code executed, which can detect when the asynchronous operation has started before it has completed. And at some point, it is completed, and then Boost.Asio calls me, tells me it is done. And how does a library like Boost.Asio do it? When we call a function like doAsync, we typically pass function pointer or a function itself to doAsync, and a library like Boost.Asio will then call that function, and that's when we know that the asynchronous operation we started is done. So at this point we can execute our code again. We are the ones defining done, and then we see the function call returns, and the event loop in Boost.Asio takes over again. Because it is of course possible to initiate a couple of asynchronous operations, not just only one. And the event loop in Boost.Asio is always running, trying to find out when asynchronous operation is complete, and then it tells us. Now there are a couple of things which are important when you look at this slide. One thing I guess is very obvious. If you start using a library like Boost.Asio, your program structure changes. Up until now we call synchronous functions. And you can easily tell when you look at your code what's going on. You call one function after another. And you use a library like Boost.Asio, you still have a couple of functions. But they are all passed somehow as event handlers to functions like doAsync. And at some point these functions are called by a library like Boost.Asio. And it's not that obvious anymore if you look at source code in which order these functions are maybe called. It all depends when the asynchronous operation is complete. Another thing which is important, or maybe something you also wonder about, I was telling you that this blue arrow going down here is one thread, and I assume we have indeed only one thread in our process here. But it's still somehow possible to initiate an asynchronous operation, and this asynchronous operation is somehow, at the same time executed. At some point the asynchronous operation is done, but we have no other thread here, so how does this work? Who else is that who is going to complete our asynchronous operation? And you see already that there's something going somehow happening at the same time. There's kind of concurrency, and that's the next thing we have to think about. At least when I hear concurrency, I also think threads. But in this case, I want to make it very clear, also after you have maybe heard about that async function yesterday, in the C++11 talk from Rainer, that Boost.Asio has nothing to do with any thread. So there's no thread created in the background, something async does in C++11. So how does it work? How does Boost.Asio make it possible to somehow concurrently execute and complete an asynchronous operation? And when do I use a library like Boost.Asio, and when do I use make thread? Now this is now about Boost.Asio, and the rule of thumb is that you use Boost.Asio to access resources concurrently outside of your process. So what I think of when I hear Boost.Asio, I imagine that I have my process on the one side running on the CPU. And the process wants now, for example, to send some data over a network to someone else. So the process accesses another component in my system, the network card. What my process says to the network card is, the network card, I have here a string, please try and send this string out to someone else. The network card says, okay, I'm giving it a try, but it will take some time, I still have to figure out whether I can do it or not. And then my process says, alright, but I'm not going to wait now, just do your job, and tell me when you're done, tell me when you manage to send out the data over the network, or maybe fail. So at this point, I have another component in my system, the network card, and the network card is basically doing stuff while my process is running on the CPU. That is the other component which can complete the asynchronous operation. And there are other components in our computer, not only the network card, but for example the serial port we can talk to. We can tell the serial port, please do something for me, try to send some data, but I don't want to wait, I want you to tell me when you're done. Do it at the same time while my process continues to run on the CPU. Or communicate through a pipe with another process running on another CPU or another port. Again, things happening at the same time outside of my process. And all the examples I just gave you, talking to the network card, talking to the serial port, talking maybe through a pipe to another process, all of this is supported out of the box by Boost.Asio. And I also make another, or I changed the diagram a little bit. You see now that I have here 3 arrows. In this case, I initiate 3 asynchronous operations, like talking to the network card, talking to the serial port, talking maybe to another process. All of this is initiated after another, and then I call the event loop, and Boost.Asio processes now some code to find out when these asynchronous operations complete, and it tells me. It calls then every time the done function, and I can somehow react to these completed asynchronous operations. Now, when do we do threads? I guess that's an easy question to answer. You probably already know the answer anyway. We have resources inside of our process. We have, for example, a bunch of numbers we need to process, and we find out we can split the numbers into 3 groups. So we can create then 3 threads. The threads can process 1/3 of these numbers, and we find out that can be done concurrently within our process. In this case, the numbers we want to process, that is the resource within our process. There's no point to use Boost.Asio here. That is where we would use threads. It is actually possible to use Boost.Asio and Boost.Thread or other threading library if you like. If you on a Boost.Thread, if you like to use this library at the same time. And you have another slide later in this presentation where you see that you can combine these 2 libraries, so it's not always the one or the other. You can indeed combine it to improve the efficiency of the programs. Now these were some concepts. Now let's look at some code finally. Here we have a program where I use Boost.Asio. It's not entirely complete. You would need to include a header file here, otherwise you can execute it. And as I was talking about some concepts before, like event loop, initiating asynchronous operations, handlers, we should find these concepts here in this code again. And again, it's not too difficult to spot them. If we look at the function there, the function is already called handler. So that's one of the functions I'm going to use, which I want to be called when an asynchronous operation completes. And you see that this handler function here has a parameter of type Boost system error code. That is rather typical for handlers used in Boost.Asio. All the handlers you use there always have at least one parameter of this type. And the reason is that when a handler is called and then a synchronous operation completes, you don't know whether it completes successfully or whether something went wrong. That's where you get this parameter, and one of the things you always do in these handlers, you check, of course, first why your handler is called. Did the asynchronous operation really complete, or did something break? You should also see here the event loop somehow, and the event loop is here within the object which is called IO service, and the function which I call, which passes over the thread to Boost.Asio, the function which doesn't come back, that is the last line here in this program, that is IO service run. So IO service run is a blocking function. At that point, Boost.Asio takes over and tries to find out when a synchronous operation is complete. At some point, I also need to start an asynchronous operation, obviously. I guess you have also seen that line already. That is the async underscore wait. All the asynchronous operations in Boost.Asio are initiated with member functions. So you see that you have to call async wait on an object called timer. The timer object has the type deadline timer. And deadline timer is one of many classes in Boost.Asio provided to initiate asynchronous operations. And when you look at the documentation, you go through the classes. All these classes have functions which are always called async underscore something. So you can easily identify the member functions you need to call to initiate asynchronous operations. Now, what does this deadline timer do? Well, it's a rather simple class, and it's a rather simple asynchronous operation. It's one of those exceptions where you don't access any resources outside of your process. So I chose this class now to keep that program, of course, as simple as possible. So if you execute this program, nothing's going to happen for 5 seconds, and then the program exits. Why does it exit? I told you that when I call IO service run, Boost.Asio takes over. There's an event loop executed in Boost.Asio to find out when a synchronous operation is complete. Run does indeed at some point return. And the run returns when Boost.Asio detects that there are no outstanding operations anymore, that there's nothing else Boost.Asio needs to wait for. So when I run this program, at first my IO service object is created, that is where the event loop is embedded. Then I access the deadline timer, because the deadline timer is the class I need to use to wait for something. In this program I just want to wait until one time expires. All the classes in Boost.Asio, like deadline timer, always expect as a first parameter an IO service object. You need to access somehow the event loop in this IO service object. And in this case I need to pass a second parameter to the constructor, because I need to tell the deadline timer how many, in this case seconds, it should wait until something expires. And the Boost libraries, of course, use each other. So I use here something from the library Boost datetime, with Boost POSIX time seconds type. And the deadline timer knows now that it should expire after 5 seconds. I initiate then the synchronous wait operation. I call async wait. I pass here a handler, a function to async wait, telling Boost.Asio, please call my function handler when the 5 seconds expire. And then I pass over the code, then I pass over the thread to Boost.Asio and say, okay, now run your event loop so you can figure out somehow when the 5 seconds expires. Now, if you work with Boost.Asio and you look at the documentation, part of the job is to find the right class. There are many classes in Boost.Asio. As I said before, you can access the network, you can access the serial port, or you can maybe somehow talk through a pipe with another process. Deadline time is one of them. It comes down to the asynchronous operations you want to initiate, which class you have to pick. So deadline time on the class just to wait for time to expire. I also said that all the member functions are always called async underscore something. Easy to remember, easy to find the functions. And also important to know, run, while it is a blocking function, it returns at some point, so it's not that your program hangs there and you need to exit it somehow. It returns and there are no outstanding asynchronous operations anymore. So we see here a couple of other classes which are provided by Boost.Asio deadline timer we just have seen. There's also another class called IP TCP acceptor. That class is used to exact incoming TCP/IP connections. So if you were to create a web server, you would use this class. We have a class called IP TCP Resolver. You can use that class to resolve host names, to map host names to an IP address basically. You can call functions on an IP TCP socket class to read and write data over a network. And you also see here how all these functions are called to initiate asynchronous operations with async accept, async resolve, async read some, async write some, and so on. If you are more interested in the acceptor, resolver, socket classes, there's another presentation after the breakfast where I continue here and talk specifically about network programming with Boost.Asio. So if you look at the Boost documentation, if you are maybe trying to find a network library, I think the first thing you always do is you're looking for something like Boost Network or Boost Net or Boost Socket. Nothing to find. And it comes down that you have actually to use a library like Boost.Asio in order to have access to some network components. And the reason is that network operations are really a prime example for asynchronous operations. That's where the library really comes from. So there's a big part in Boost.Asio which is really about networking only. Now there's also a Boost.Asio mailing list. And if you go to the Boost.Asio mailing list and you talk about event loops and classes like deadline timer, everybody knows you are a newbie. So you should get familiar with the Boost.Asio terminology. And the IO service class here is not called event loop, even so I started by explaining this to you. We call this thing an IO service object. And classes like deadline timer, they have also a name, they are called IO objects. If you write a program and you access Boost.Asio, you always have at least one IO service object in your program. You have also, of course, always at least one IO object in your program. Again, for easy understanding, think of the IO service object as being the event loop. Think of the IO object as being the one to provide access to the asynchronous operations. But that are the terms used by Boost.Asio developers. You see that the IO service object will always pass as a parameter to the constructor of an IO object. The reason is that the IO object really needs the IO service object. And why does it need it? The IO service object provides IO services. That's where the name comes from, and that's the third very important concept in Boost.Asio. It's very important, but it is not visible in user code. We only have IO objects and IO service object, but there's something else in Boost.Asio called an IO service. It is important for two reasons to know that there's a third concept. One reason is when you look at the documentation, you see many different classes. You might not be sure which of the classes you really have to use. There are a couple of classes which are all IO services you can just ignore. The other reason why you should know about the IO services, if you really want to extend Boost.Asio because there are some asynchronous operations missing, you want to add a new one. You don't just create an IO object and put the entire implementation in the IO object. You create something else in the background called an IO service. And if you do that, you use the pattern used within Boost.Asio to structure the library code. So on the one hand, if you look at user code, we have IO objects like the deadline timer. It accesses an IO service object, and it uses an IO service provided by that IO service object. And if you look into the IO service object implementation, it's basically a set of services. A deadline timer knows it needs to use a certain service, so it looks into the IO service object, it checks whether the service exists. If not, it is created and registered in the IO service object. If it exists already, the IO service, because we had a deadline timer before in the code, it just reuses the existing IO service. So it's really a set of IO services. But if you look at the code in the deadline timer, you see there's really nothing going on. The deadline timer just forwards the member functions, all the calls, to its IO service provided by the IO service object. So the main functionality, the really important part in Boost.Asio, where all this stuff is somehow implemented, that is really the IO services somewhere in the background, something we don't see in user code, but which is in the documentation and which is of course still in the library. It could be important to know if you really want to extend Boost.Asio and add your own asynchronous operations. Another picture of the entire Boost.Asio architecture. Here we see our I objects. You can use as many as you like in your program. You always have then one IO service object. You have seen all these IO objects typically get a parameter to the IO service object in their constructor. And then these IO objects access through the IO service object their IO services. And you don't need to do anything about it really. The IO objects know which IO service to access. So some of them have their own IO service. Other IO objects even share the service. So I'm talking here about different types, not about different instances. So there can be different types sharing the same IO service. To make it a bit more concrete, here are some types from Boost.Asio. You see here in the corner the basic deadline timer, the deadline timer which we use in the central program, and it knows it needs to use the deadline timer service. If you look at the code there, basically empty, it's just calls forwarded to the IO service. And there's another example with two IO objects which share an IO service. The basic stream socket and the basic socket IO stream, they both access the IO service stream socket service. I quickly want to show you the documentation that you understand why it made hopefully sense to explain you a little bit about the architecture of Boost.Asio. That is the reference of Boost.Asio, and if you scroll it down on the first side, okay, my god, lots of pluses, which one shall I pick? And you have here a couple of sections. So here's a huge section about networking, here's something timers, serial ports, and so on. So it's a little bit grouped depending on which external resources outside of your process you want to access. And you see that there are again sections within these sections. One group is called classes, the other one class templates, services. Here again, classes, class templates, services. Classes, class templates, services. All the same. What you are interested in as a user of Boost.Asio, you are interested in only the classes. These are the IO objects. Here, the services you have just learned, they are somewhere used in the background. But fortunately, if you use a class like the deadline timer, the deadline timer knows already that it has to use the deadline timer service. And nothing for you to worry about as a Boost.Asio user. If you look at these classes are all based on templates. So the deadline timer is based on the basic deadline timer. And the basic deadline timer has a default service, which is the deadline timer service. So if you just use the deadline timer, it's the same as if you use the basic deadline timer with the deadline timer service. So this breaks down the reference of Boost.Asio. As an Asio user, just look at the classes. Imagine that these classes are not called classes but IO objects. That's where you find your async underscore whatever member functions, and the templates and services. Yeah, you can ignore them again. Now let's look a little bit more at code. What else can we do with Boost.Asio? Here we see an example where I use the deadline timer twice. So I want to initiate two asynchronous operations before I pass over my thread to Boost.Asio and call run. How does it look like? We have again one IO service object. We instantiate the deadline timer twice. We pass the IO service object as a first parameter again to the constructor. I say both timers should expire after 5 seconds. Then I initiate the asynchronous wait operations. I call async wait, pass my handler to these functions, and I call IO service run. And at that point, Boost.Asio takes over and should detect when the time expired and when my handler should be called. Now obviously after 5 seconds, IO service finds out, okay, there are two asynchronous operations done and complete. What happens? At first the one handler is called, then the other. Even though these two timers expire in the same moment, it is not possible for Boost.Asio to call my two handlers at the same time. They cannot be executed concurrently because there is still only one thread in my program. So don't mix it up with the async function from C++11 where we have a thread in the background. I pass the thread over to Boost.Asio by calling IOService1, and from that one thread only, Boost.Asio will call my handlers, and even so there are two handlers which should actually be called in the same moment. They will be called one after another. Here we see an example where I use Boost.Asio together with threads. I actually see a Boost thread, and you see here the class Boost thread which I instantiate. I use here a lambda function. It could be my presentation yesterday. You can now assume that everybody knows lambda functions. And I call now here run on the IOService object in my thread, which I just created, but I also call it in my primary thread. Now at this point I have obviously two threads running, and in both threads I access the IOService object and call run. Here in this program I use only one timer. So after 5 seconds this one timer is going to expire. Boost.Asio sees, oh, I have two threads, and it will call my handler function on one of these two. We don't know in advance on which one, but Boost.Asio can now make use of two threads, and it calls handler on one of these two threads. If you were to modify this program and we access the second timer, just like on the previous slide, and the second timer is also going to expire after 5 seconds, then it is indeed possible for Boost.Asio now to call the handler function once on the one thread and the second time on the other thread. So if you think again about this big picture, that you use Boost.Asio to access resources outside of your process concurrently, to make use of network cards, serial ports, other processes, which all can do their job at the same time while your process is running. If you imagine that you can use with threads the multiple cores in your machine, you can provide these threads and then these cores again to Boost.Asio to execute handlers at the same time. You can try to benefit from all the components in your system, which can do something at the same time, in the same moment. So here Boost.Asio can work together with threads. So imagine you have now created a program, there are a lot of asynchronous operations, there are a lot of threads, everything is more or less happening at the same time. But there are two handlers which share a resource. What you could do now, you could of course access the usual classes and other helpers, library like Boost Thread provides, like mutexes, semaphores, and whatever else there is, condition variables, to synchronize access to the shared resource. But if you can identify the two handlers, which you know shouldn't actually run at the same time because they would access a resource at the same time, which you don't want to happen, then you can also use a helper class from Boost.Asio, which is called Strand. The class is actually within the IOService class. What you do, you instantiate this class, you create a strand, you pass the IOService object as a parameter to the constructor, and then you use that strand to wrap handlers. You see this here, I don't pass my handler anymore directly to the async wait function, I wrap it in a strand, and because I use the same strand here for my handlers, what's going to happen after 5 seconds when Boost.Asio detects that these two timers expire, Boost.Asio realizes it would like to call the two handlers at the same time on the two threads it got from me. You see, I still have my Boost thread object here, and it's still called IOService1 twice, so Boost.Asio still has access to two threads. But Boost.Asio sees that the two handlers it should actually call, or it wants to call, cannot be called at the same time. They are wrapped by a strand. So in this case, these two handlers are executed one after another. It's a very simple way to make sure that certain handlers are not executed concurrently. Most of the time you want to do this, you want to ensure that everything happens concurrently, but if you want to avoid this, don't automatically think of mutex and everything else, what there is. There's something else in Boost.Asio which can make it rather simple. There's another thing, another helper class in Boost.Asio called work. I told you that when you call the function run, that run is a blocking function, run doesn't return. When you call run, the event loop in Boost.Asio takes over, trying to find out when asynchronous operations are complete. And at some point there is no asynchronous operation to wait anymore, and then run returns. If you want the event loop to continue to execute, you don't want run to return, you can create work for the event loop to do. And you can instantiate the work class provided by the Asio service class again, class version another class. All you need to do is you instantiate this class, you pass the Asio service object as a parameter to the constructor. And even if there's no async underscore something function you ever called, if there's no outstanding asynchronous operation to wait for, Asio service run will not return now. So there's work to do. Normally what you do in programs, when you use the class work, you create it new, put it on the heap, and you destroy it with delete at some point. And when you destroy it, the Asio service object finds out, okay, there's no work to do anymore. And if there's no outstanding asynchronous operation, Asio service run returns. Now there are a couple of links I want to give you if you want to find out more about Boost.Asio. One thing I told you already before, there's another presentation in 30 minutes, especially about the network I/O objects. Well, most important, of course, the Boost.Asio documentation. Then there were two presentations in 2011 at the BoostCon, one from Chris Kohlhoff, the other one from me. Chris Kohlhoff is the guy who created Boost.Asio. What is maybe also important to know, the library was created outside of Boost in the beginning, and that library outside of Boost is still maintained and developed. So if you like, you can just take the library Chris has put on his website. If you don't want to take all the other stuff from Boost into your program, you don't want to have dependencies on many other Boost libraries, you can just take the library from his website. And I think his talk was called Thinking Asynchronously, because his website is called Think Async. So it's here, this think-async.com, and there you find the, well, Asio library, not the Boost.Asio library, but the Asio library, without any dependencies on other Boost libraries. I also want to point you to a chapter in my online book. It's available in a couple of languages. Okay, one of those Chinese. Okay, no one. And last but not least, there's also a paper which was created by Chris for the C++ Standard Committee. I'm not sure in which presentation it was mentioned yesterday, was it Rossmann, that Asio is 2022? Yeah. So you too often you wait until 2022, or you use Boost.Asio or the Asio library from think-async.com as of today. Otherwise, when you look at this paper, it's also a high-level overview, so it's not getting too technical, not getting too complicated. Another way to find out a little bit more about how Boost.Asio works. Ooh, very good timing. We still have 5 minutes, so it's your chance to ask some questions. If you prefer to have breakfast, just be silent. Oh yeah, there's one question in the background.
For the multi-threaded approach, why should we, or how does Boost make the decision of which thread to run to handle it?
Yeah.
Why should I trust its scheduling?
Depends a little bit on how the event loop is really implemented by Boost.Asio. When I say event loop, I didn't tell you yet what system API function is really called there, but maybe you imagine already that when you look at Linux or Unix, other poly systems, it's select, call, equal, typical functions you use there. If you use Windows, it's IOCP. And it depends now on the system API function, what's really happening there. And if you use IOCP on Windows, for example, you indeed have a blocking function on the many threads which is passed over to Boost.Asio, and it depends on the Windows operating system which ones of these blocking functions returns and which thread is going to wake up and call the handler at the end. And in the other cases, when it comes down to select and what else there is on the calling systems, I'm not entirely sure how the implementation looks like there, but it could be that also this function is called on multiple threads, and it just comes down to the operating system where in which thread this function comes back.
That's a similar question. In which platforms will Boost.Asio across which Unix platforms, like IE,
Yeah.
HP, like Windows?
Yes, I would just refer to the homepage from Chris, and here is the list of supported platforms. Yeah, there are some platforms which may work.
More questions?
If I want to use Boost.Asio in a system with a graphical user interface, the tool for building this graphical user interface will typically have its own game loop. So how would I approach this problem? Graphical GUI and a graphical Asio or something else?
I think that is also what I would think of, because when you call Asio run, yeah, it's from that point on Boost.Asio who's going to own and use this thread. There are other functions you can call, not run, but something like run one or run once, something like that, a function which executes in one handler and comes back, but it's a little bit like calling. But yeah, if you really have multiple event loops, I guess the most obvious solution, or maybe the most naive solution, would be to use multiple threads.
When you talk about the work that can pass to iOS services, is there a way to stop the work by deleting it?
Yes, you can delete a work object anytime, and then the event loop finds out, okay, no work to do anymore, and iOS service run can return.
Okay, is there another way?
Well, there's no explicit member function on the work object. It's just that you create the work object with new, and then you call it.
More questions?
Right. Thank you very much, and enjoy breakfast.